real quick in review, what we're going to do is we're going to do lab 11 on Tuesday. Notice that it's out of order in your lab packet. It's actually after lab 12, I think, in the order that I printed it accidentally, but it's called molecular structures and Lewis structures or something like that, or molecular geometry and Lewis structures. The other thing we talked about, since Jess just walked in, is my office hours today will be at 6 p.m. if people want to come by here in Kramer 107 or whatever room this is, some room. And then we're thinking about a test next week on Tuesday. So let's take a look at chapter 11 then. And now we're getting into some what I call a deeper understanding of chemistry. It's chemistry that you already know how to do, but it's chemistry that maybe will have a better explanation of why things occur, or a deeper understanding. And we want to start off by talking about Lewis structures. And actually, let me double check. Maybe we'll change. Yeah, we kind of have to do Lewis structures first. And what Lewis structures are is an easy way to represent the valence shell electrons. And we represent them as a dot equals 1 electron. And then we haven't talked about it yet, but a dashed line is going to represent 2 electrons in a shared bond. And that's really the basics of Lewis structures. And we see that it follows the normal rules, meaning that all molecules will obey the octet rule. Now, we might cover this in lecture if we're bored, or just to let you know that there's more to it, but there are actually 3 ways you can violate the octet rule. I'm very careful about the molecules I put on your homework and tests and stuff, so very rarely do they ever accidentally violate the octet rule, or even our standard set of rules for drawing Lewis structures. But I got to be honest, occasionally one slips in there, and so if something seems really out of whack, just realize I might have made a mistake. But I think I actually have all the mistakes taken out by now. But I won't make any promises, since sometimes I find a mistake, say I'm going to take it out, forget to take it out, and then think I did it. Because just that's the way I work. So all molecules will obey the octet rule. And what we're going to do is we're going to represent the valence shell electrons as simply dots. So for instance, hydrogen is 1s1. It has 1 valence electron, so we just represent it as a single dot. Or if we go down a column, for instance, lithium has 1s1, 1s2, 2s1. Again, we're just going to count the valence shell electrons, so we're only going to show that electron in that s orbital. And the idea is that we can ignore the inner shell electrons. They're already in complete orbitals. They don't interact, they don't form bonds, they're too deep in the molecule to sort of interact with another atom. So then what if I did, say, magnesium? That's 1s2, 2s2, 2p6, let me check, 3s2. How should I draw that? 2 dots. Now, there's different schools of thought as to whether you should pair the dots up or not. In general, I mean, if you think about it as really representing the 3s2 electrons, those electrons are in the same orbital, right? So if we consider the side of the atom that they're on as being the same orbital, then we should draw them paired up. But I'm going to suggest that in general we show them unpaired. There's a minor variation to Lewis structure which shows, it's called valence bond theory. It's not minor, but it shows that all 4 orbitals can be thought of as the same for normal s and p orbitals for normal molecules like we're dealing with. We're not going to go into the theory. We're just going to say that all the s and p orbitals in the outer shells behave the same way and not worry about it. So magnesium has 2 valence electrons. If I go one more over, I get to say boron. And boron has 1s2, 2s2, 2p1. So how many valence electrons does boron have? 3. So I'm going to put 3 dots. And so the idea is that we can represent these, instead of drawing 1s2, 2s2 ad nauseum and getting tired of drawing it, Instead, it's much easier to draw things as dots. Carbon then is 1s2, 2s2, 2p2, so we're going to draw 4. Nitrogen is 1s2, 2s2, 2p3, so we have to finally pair up a set of electrons. Oxygen, 1s2, 2s2, 2p4. I'm going to have to pair up 2 sets of electrons. And it doesn't matter which set you pair up, meaning if you want to draw it like that, or you want to draw it like this, or you want to draw it, you know, like this with the lone pairs here, they're all the same. There's no directionality to anything. It doesn't matter where you put the dots to a certain extent. And then we've got fluorine, which is 1s2, 2s2, 2p5, so that has 7 valence electrons. And we just leave 1 empty. And we could put neon and argon in those and show that they have 8 valence electrons, but to be honest, they don't form any chemical reactions. We don't care about them, we don't use them for anything, so why bother? So what Lewis structures allow us to do then is to show how an ionic molecule is formed, but it also allows us to show how molecular bonds are formed, or sharing of electrons, which we haven't got to. So let's take a look and see how Lewis structures can explain something that we already know, which is how ionic molecules form. For instance, we know that if I take sodium plus chlorine, what's going to happen? Yeah, we get NaCl. And what do we know about the sodium? It really has a +1 charge, and the chlorine really has a -1 charge. So we can show that with both Lewis structures, and we can also show that with our valence shell electron pictures. So for instance, sodium is 1s2, 2s2, 2p6, 3s1. And chlorine is, I'm going to draw it lower just because I'll run out of room otherwise. Maybe I should have picked fluorine, it's easier, but 1s1, 2s2, 2p6, 3s2, 3p5. And notice that, you know, this has 1 valence electron. This has 7 valence electrons. And so if we're thinking about that octet rule, remember everyone wants to have 8 electrons in their outermost shell. Well, the logical thing to happen is the sodium gives up an electron and the chlorine gets the electron. And that's what we already know. We know sodium has a +1 charge. We know chlorine has a -1 charge. So if I look at sodium on the other side, then it's 1s2, 2s2, 2p6. It's got an octet. And I have to say I tend to anthropomorphize, or however you pronounce that word, some of this chemistry and simply say that it makes it happy, meaning it obeys the octet rule. We know that that's extremely stable from quantum mechanics, and you know, we could say that every single time. It satisfies the octet rule and is quantum mechanically stable, but that's boring, so I just say it's happy. It's also a lot easier to say it's happy or sad. So that's what the little smiley face means. It means it's happy. It's satisfied its octet. Chlorine looks like 1s2, 2s2, 2p6, 3s2, 3p6. It also has its octet, so it's also happy. It's satisfied, it's chemically stable. We expect sodium chloride exists. We even expect that it might be tasty on French fries. And then if we want to show that with Lewis structures, well, it's even easier than writing the 1s2, 2s2 stuff. We just show sodium with 1 electron on it. Chlorine has 7 valence electrons, so we put 7 dots on it. And then on the other side, sodium has lost it, and so we show gaining or losing electrons with some brackets. And then chlorine, of course, gained that electron, so chlorine now has 8 dots around it, and it has a minus charge. So the brackets indicate ions. Now I have to admit, we're not going to do Lewis structures to show how ionic compounds are formed or write reactions using Lewis structures, except for maybe, well, okay, guaranteed a test question at some point. We know normally we're just going to write Na plus Cl goes to NaCl and be happy, but you know, we can show it with this, and it does give us a deeper understanding of why these reactions happen. And it's sort of an after-the-fact explanation, but I think it also makes a nice transition into understanding why molecular compounds have to form. So let's take a look at one more example. Yes?
So how does the octet roll when they get on this side? Because they're in the same spot on the...
How did they not meet the octet rule, did you say?
Over here, sodium only has one valence electron.
Right.
And how it is over there, it has 8.
Well, see, it's now down one shell, right? So the second shell is filled. Oh, you mean over here? Well, which, I guess, are you talking about the top structure or the Lewis structure?
The top one.
Right, so it's got 2s2, 2p6, that's completely filled, right?
But where did you get that from? Did you just find sodium?
Oh, well, I mean, that's what it had before the reaction occurred, right? It was.
So you just take off that one.
So I literally took that 3s1 electron and put it down on chlorine. Just like if we think about it, this electron on sodium is really going to the chlorine. It really is gaining and losing electrons. Okay, what if I do, say, barium plus iodine, and we need 2 of those, goes to barium iodide. And actually, I guess we technically write it like this. But how can we show that in terms of Lewis structures? Well, how many valence electrons does barium have? Look on your periodic table, see what column it's in. It has dose. Does everyone see where I'm coming up with the 2? Yes, no? Some people don't have periodic tables out. I'm going to assume that the people that don't have periodic tables out have it totally memorized.
It's because the last thing is 6s2.
It's in the second column, right? And then it's because we know barium forms a +2 charge. That's kind of true. But what we're going to find is when we have molecular compounds, we don't know what charges to expect. So we're going to have to count the valence electrons. I have 2 iodines. And how many valence electrons does iodine have? 7. And again, it doesn't matter where you put the pairs of electrons, which one you leave empty. And so notice it kind of makes sense that barium would lose 1 electron to 1 iodine and lose a second electron to another iodine to form barium +2. It has an octet then, because the electrons are 1 level down. And then each of the iodines also has 8 electrons around it, forming its octet, and we have 2 of them. And so, you know, we throw in a lot of extra brackets and things like that in here to show that with Lewis structures, we're probably okay with just writing barium plus iodine forms barium iodide and maybe throwing some states in if we're in chapter 8. But, you know, we can show all of this using Lewis structures. Okay, so one of the things that we've noted is that for ionic compounds, they tend to gain or lose electrons. And then the bond is basically that electrostatic attraction. Because we know that opposites attract. And we said that one of the big differences between that and molecular compounds is that molecular compounds share electrons. And we've left it at that. We've just said, take this on faith. Well, now we can, since we know where the electrons are in atoms, we're starting to understand the concept of the octet rule and valence shell electrons and things like that. We can actually start talking about what we mean by sharing electrons. So let's take a look at sharing. So if I've got a hydrogen, and it's got 1 valence electron, and I have, could I go back for a second, did you say? Sure. Oh, we should say, by the way, congrats to Jay. I know they won against Lamar, right? And that's good. I think that's the first time we've ever beat Lamar.
Really?
And I think so. At least in my recent memory. How about that? Now, my memory might be bad since I'm getting old and crotchety. But, you know, it's that. Now, I know you lost to Colby.
Mhm.
And then did you beat some other team, I heard? So you went 2 for 3?
30.
What? No.
By 30.
By 30? Well, must have been some high school then.
It was an NAIA baby.
Never even heard of that. Okay, so we got hydrogen plus hydrogen, right? Now, actually, let me not use hydrogen. Hydrogen's bad because hydrogen's an exception to the rule that I forget to mention, so let's use fluorine. It means we have to draw a bunch more dots, but that's okay. Now, what do we know about fluorine, really? It's a diatomic, right? So we know for sure the chemical reaction occurs, that fluorine plus a fluorine will give us an F2 molecule. But the problem is if we think about it in terms of Lewis structures, well, if one of the fluorine gives up an electron, then it's only got 6 valence electrons. And the other fluorine would have 8 valence electrons, right? So this guy's happy. Oops. This guy is sad. And so that's not how it occurs. And the other thing is how would you tell which fluorine should give up the electron? I mean, they both technically are identical. They both technically want an extra electron to complete their octets. So one fluorine is hardly likely to give up a second electron. So instead, so we can't gain and lose electrons to reach octets. And maybe we should say we can't always, meaning we certainly can for ionic compounds. So what that means is that we have to share. And pictorially, the way we represent that with Lewis structures is the starting point's the same. We just have a bunch of fluorines. But now we show that the fluorines share one set of electrons between them. So remember that line equals 2 shared electrons. And then the way we count the valence electrons is shared electrons count towards both atoms. Oops, atoms. And so if I'm thinking about the valence electrons around that fluorine, I count the 2 electrons. And if I'm counting the valence electrons towards that other fluorine, I count the 2 electrons. And so now this has 8 electrons and 8 electrons. And what it's really saying is that it's got 6 all by itself plus 2 shared. And this one has 6 by itself and 2 shared. And it turns out that sharing an electron is a lot better than losing an electron. It's not as good as gaining an electron, but it's better than losing it. And so sharing is that middle ground. It's better that you get a little bit of an extra electron, you get that much closer to an octet, than that you completely lose an electron and are nowhere near close to an octet. And so that overlap sort of represents the bond between the 2 fluorine atoms. You can kind of think about it in terms of what the electron orbitals really look like if you're good at drawing. And I'll draw a picture here in a second, but I see 1 or 2 people still writing. What's the question? Yeah, the shared electrons count towards both atoms.
So is that like just a little minus sign?
Which, this dash right here?
Yeah.
Well, it's a big bar compared to a minus sign. Like, so if I drew fluorine minus, I draw it like that. If I'm drawing a fluorine bond, it's bigger. Plus, the location of it is different. So unfortunately, we use a dash for 2 different things, right? Actually, we use it for a minus sign. We use it for a hyphen in English. Dashes are pretty darn useful, right? Sometimes I think we overuse our symbols sometimes, and that can be confusing occasionally in life. So if we want to think about it in terms of orbitals, well, fluorine is normally 1s2, 2s2, 2p5. And so what that means is if I kind of draw the orbital diagram for it, you know, there's my 1s, 2s, 2p orbitals. These are filled. These are filled, and that has one electron like that. And then if I have a second fluorine, it also has a similar electron shell diagram. I'll draw it in red. Oops, like this. 1s, 2s, 2p. Lots of paired electrons. Now notice I drew that arrow down because what we're saying is that they're sharing that electron, that sometimes that electron is in one orbital, sometimes it's in another, and we learned that really we have to eventually go to molecular orbitals, and sometimes that one is there, so this one is also shared. So those are our shared electrons. They kind of belong in both sets of orbitals. Or if we think about it as that's really being a p orbital, what we really get is we get one fluorine like this and another fluorine like this. And just up here, I guess, just to remind yourself, what a p orbital normally looks like this, right? So what happens with those shared electrons, well, actually here, let's do it like this, I guess. With those shared electrons is there's a big overlap here and a little bit like this, and this one has a big overlap and then a little bit like this. That's where those shared electrons are. Here's my two fluorines. Or what we really find kind of happening to that picture is we get a huge amount of shared electron density and then a little bit that's not being shared. So those represent the shared electrons. So we can draw orbital pictures. We can actually do the quantum mechanic calculations and come up with what happens when I literally physically overlap two orbitals from a different atoms and show that the electrons can actually be shared between both sets of orbitals and that they kind of merge. If you want to think about it in terms of music, because we've talked about wave-struck nature of things, if you have two chords that you strike at the same time, they make, what, a harmonic or something like that, or I don't remember. But you know, you can play more than one chord at a time, right? You can kind of think about it as the mixing of those two waves like that, which allows the electron to be in both places at once. Or I've heard some other people say that, and I don't know colors very well, but you know, if you take red and you take green and you mix it together, you get purple, right? Blue? Blue and red. Okay, fine. Blue and red is purple. So one electron is blue, one electron is red, but the mixture of them is purple. They can exist together and they can form that bond. So we can have that sharing of electrons. And then what we see is that, for instance, if I take, say, oxygen plus oxygen, how many electrons does oxygen have? Has 6 valence electrons, right? Now, what do we know happens? We know O2 exists as a molecule, right? So we should certainly be able to draw a Lewis structure for it. So if we share some electrons, share one set of electrons, then we get something that looks like this. Oops, that's supposed to be 2 dots on top. And then an electron like this. And if I count up the orbitals, then this has 7 electrons, and that has 7 electrons, meaning I've got 5 unshared for each of them, 2 shared, that's 7.
Why would you do a double bond?
Does not, there you go, satisfy the octet rule. So you're right, that doesn't work, right? So what happens is we have to share more electrons. Meaning we can share more than one set of electrons. So if I share another set of electrons, like Erin says, because she's had some chemistry before, we form what's called a double bond. So here I'm sharing 2 sets of electrons. And what I mean by sets is 4 electrons, and it's called a double bond. And if I take a look at how I'm counting the electrons, then I draw it kind of like this. And each one has 4 unshared and 4 shared electrons to make 8 electrons and make its octet. Everyone's happy. And then, of course, if we can make double bonds and share 2 sets of electrons, what do you think we can also make? Yeah, so for instance, if I take a look at nitrogen, it has 5 valence electrons. Do I need to go back? We should have a speed writing class. I'll teach that. Anyone else have an exciting weekend? Finished a book. Is it the Book of Mormon? Gosh, what was I thinking? Oh, maybe I shouldn't put this on tape, but this is an interesting time to ask this question. So someone told me this weekend, and I don't know if I should think it's funny or not. So, Jay, I hate to put you on the spot. Are you comfortable with racial issues?
Yeah.
Okay, so if I said, you know, if someone said, so who do I give this to? And I said, the black guy. Are you going to be mad that I point out that or something?
Am I the only black guy?
Well, you're the only one in the room, so seems fair, right?
Yeah.
Now, have you ever heard the term, so someone said this to me, and I don't know if I think it's funny or not. I mean, obviously, you know, like, I think black guy's okay to me. Now, nigger, probably not a good word, right? But someone else said, oh, he's shaded. Or he's something like that, and I'm like, what is that? Is that like politically correct way of saying he's black, you know? I don't know. Is shaded okay? Is it better than black? I'm sorry, I have to laugh.
That's just weird.
I can't remember if they said, I'm struggling to remember exactly what they said, because seriously, I'm like, you mean he's black? And she's like, yeah. It was either shaded or dark. He's dark. But I mean, seriously, you know.
Some people are darker than others.
Yeah, that's true. But I'm pretty sure she said shaded, and I was just like, wow. What? Well, it says some context to that. But then again, there's the Dark Knight, and he's a superhero, so I don't know. Anyway, totally off topic. I was just kind of curious if people had heard that term before, or
I've never heard that.
yeah, maybe that's the cool new way to call black people. I don't know. It's okay. I thought the whole thing was kind of silly. Okay, so nitrogen plus nitrogen. Notice that in order to share electrons, that both of them want 3 electrons, so that means we have to share 3 sets of electrons, and we get our triple bond. So here's a triple bond. We share 3 sets of electrons. And so we have 2 unshared and 6 shared. And it turns out that, you know, even though they really don't have 8 electrons in its valence shell, it's a hell of a lot better to share 3 sets of electrons with someone else than to be left without an octet. You don't ever see nitrogen. This does not exist, right? How is hydrogen or nitrogen always written? It's always a diatomic. We always see N2. And the reason it's N2 is because it's sharing 3 sets of electrons. And nitrogen is very inactive, or not inactive, unchemically reactive, meaning it's the majority of our atmosphere. It doesn't react with anything. In fact, one of the things that biologically, when we get to the very last section next semester when we're talking about bioenergetics and stuff, nitrogen fixation is one of those truly hard things to actually do, meaning it's hard to break that nitrogen triple bond. It's pretty unreactive. Now, what about this last example? What about carbon plus carbon? Does carbon form a diatomic? Yeah, it does not form a diatomic. And so we kind of conclude, not necessarily just from this, that does not exist. Meaning quadruple bonds don't exist. You can't draw carbon sharing that many electrons. It's just physically impossible to share that many electrons. To understand that truly, you have to go into what's called valence bond theory and look at exactly what happens to the orbitals. We're not going to do that. We're just going to say quadruple bonds don't exist for types of atoms that we do. Now, if you get into metal atoms and d orbitals and lots of other things, you can make quadruple bonds. You might even be able to make a bond with 5 shared electrons in it. It's conceivable, just not easy. Jay, did you say you had a question?
Yeah.
Okay.
How do you know what produces a triple bond, what produces a double bond?
We're going to find that with a lot of practice, it becomes kind of second nature. I would say that the way we do it is we have a set of rules that we follow when we're going to be building these complex Lewis structures, meaning more than just 2 atoms stuck together, in which we don't share electrons until we have to, and if we need to share electrons, that's when we make double and triple bonds. So we'll make that clear tomorrow, because we won't get to it today. But we'll walk through kind of those steps. And you'll find that some atoms, when you get kind of used to these Lewis structures, and I'll give them to you, that's what I call just rules of thumb, you'll notice that just by the sheer math of it, for instance, if we take a look at oxygen, how many electrons does it want? So it almost always makes 2 bonds. It's impossible to have an oxygen with a triple bond because it's already happy with just sharing 2 of them, right? So for instance, oxygen never makes a triple bond. It can make double bonds and it can make single bonds. And so we'll take a look at those general rules of thumb tomorrow when we draw lots of these pictures. Now we're just trying to get that idea kind of sharing down. Oh, we're going to go look at big molecules. And then second semester, you look at huge molecules. Oh, quit whining. I'm not up for it on a Monday morning. Okay, so we have something else we want to talk about. It's called electronegativity. It's one of my favorite words. I don't know why. And I abbreviate it EN because writing out electronegativity is way too much work. And this is the attractive force an atom has for electrons in a shared bond. And what electronegativity is really saying is that not all atoms share equally. That, you can split a candy bar in half and give it to 2 kids, but I guarantee you if you give it to a little kid and say, split that and give your sister half of that, he'll split it into a quarter and 3/4 and give his sister the quarter part, right, Oksana? Your kids will split it 50-50? Okay, well, if they're your typical American children, they would split it. You'd be lucky if he even gave his sister any of it, probably. Brittany, do you have a brother?
Well, it would bring me a 6th part.
Aw, your kids are sweet. I bet the best of you are rotten children that would just keep the candy bar and not even share it. How many people have brothers and sisters? Yeah, would you keep the candy bar? Would you share, Jess?
No, my brother's mean.
Yeah, see? That's what I thought. So, just like Jess's brother is mean, some atoms don't necessarily want to share electrons equally. For instance, if I take a look at, say, hydrogen and fluorine, so hydrogen has 1 valence electron, fluorine has 7. And so fluorine really wants 1 more electron. Hydrogen is okay and would like another electron. This is like Jess, who won't share. This is like her brother, who probably is a nice guy and really would share. And so the idea is that when they make that bond, when they share that electron, they're not shared equally. And so we might want to more represent it like this, where, the bonds are closer to the fluorine. That's kind of 2 big electrons. They're closer to the fluorine than they are to the hydrogen or something like that. Or really what we tend to draw a picture of is we draw it more like this, where we represent the electron density as the size of the bubble around it. So very little electron density around hydrogen, a whole lot of electron density around fluorine. So the idea is that those electrons aren't shared equally. They spend more time around the fluorine than they spend around the hydrogen atom. Now, if you take a look at all our diatomic molecules that we showed as our previous examples, they're going to share those electrons equally because they're the same element, right? But between hydrogen and fluorine, they're totally separate.
Okay, what's the difference between the one above it and
What's the difference between these two pictures? Nothing. They're just different ways to represent things. One of the things you're going to realize is that in chemistry we have lots and lots of ways to represent things. Different people like different methods, or sometimes people really like one method highlights something that another one doesn't. Like for instance, that one really does show what hydrogen fluoride looks like, that one end really has a lot of electrons and one end doesn't have a lot of electrons. And that actually kind of leads into our next idea, is that we can talk about what are called polar covalent bonds. These are simply atoms or molecules in which the electrons are not shared equally. And so I guess maybe, yeah. And so what we can do is for that hydrogen fluoride molecule, like I said, there's a lot of different ways we can represent it. We can just write HF like this and be done with it. We can draw HF like this and represent a little bit of electron density and a whole lot of electron density. Some books will even show you that you can do it like this, where that little plus sign means there's a little bit of excess positive charge, and the little arrow means that electrons are pushed this way. Or really the way we tend to do it in class is we use this little delta plus and a delta minus. So that's the Greek letter delta, means a small change. And the delta plus means there's a bit of excess positive charge. And little delta minus means there's a little bit of excess negative charge. Or what we're going to come to think about it is that we can think about that HF molecule kind of like a bar magnet. Oops, that's not a very good magnet. Oh, get those drawing skills going, Jay. So here's my magnet. And this end's kind of got a positive charge, and it's got a negative charge on the end of a magnet. And what we're going to find is that that's one of the driving forces between sort of how molecules are attracted to each other. We'll have an entire section in the next chapter probably. I can't remember if I stuck it in this one accidentally maybe. And I don't really remember or not. Oh, yep. Boy, that's the tail end of it. Man, I've packed a lot into this lecture technically. Oof, that's horrible, Jay. Well, you might not get to question number 9 on the next on homework 11C, but you'll certainly be able to do it. And certainly 11A was doable. We just finished up 11B. So we're like kind of not breaking very well in between the homeworks, but that's okay. So we can have these polar covalent molecules that have this separation of charge that causes them to behave kind of like little magnets. So how do we tell Aaron, do you remember Lewis structures? Do you like them? I think they're fun. I think they're like little puzzles.
I hate the hard ones.
You have to treat them like a little puzzle. You have to treat them like kind of like a math problem. You know, when you get the answer, you're happy at the end. There's a process that you can use. You have to be happy with a little bit of trial and error. It's kind of like putting together a jigsaw puzzle. Sometimes you just got to see if two pieces stick together. So how do we tell who wants electrons the most? Well, that's that electronegativity table on your cheat sheet. I'm pretty sure that it's still there, right? So if you take a look at it, you'll notice that, for instance, fluorine has an electronegativity of 4.0. That's the highest, and it wants electrons the most. Somewhere down in the left corner, you'll have cesium. I don't even remember what value it has, but if that's the lowest, it wants electrons the least. And so what we're going to do is we're going to use ionization energy to determine which atom wants more of the electrons than another atom. I don't know. Does someone have their chart? For completeness sakes, I want to put what cesium is. Bottom corner there. Is cesium on the chart even, Brittany? It's like, I'm going to say it's 0.7. 0 point what? 7. Dang, my brain is scary sometimes. So that means cesium doesn't want electrons very much. If you look at hydrogen, it's what, a 2.1? So, you know, it kind of wants another electron, but it's okay being by itself. The general rule, well, actually, let's do one more other thing. So we've got on one end of our spectrum ionic compounds. And that's, you know, something like NaCl. And that's where you gain or lose an electron. At the other end, we have molecular, or sometimes these are also called covalent molecules, where, for instance, if we take a look at chlorine, and just use that as our example, here we share electrons equally. And then we have this whole middle ground, which we're going to call polar covalent. That's, for instance, like, say, HCl, where there's a little bit of electrons around hydrogen and a lot around chlorine. Or really, maybe we should get used to doing it like this with the delta pluses and the delta minuses. Or if you want, draw a bar magnet. I don't really care. Negative, positive end. Put lots of little electrons around it. Where we share unequally. And so, I don't know. This is the shaded end. This is the white end. And this is the gray area. Meaning the middle ground is gray. So we said at the beginning of the semester that, well, things are either ionic or molecular. Well, turns out that that's not quite true. Things are really either ionic, molecular, or there's that huge middle ground, which is called polar covalent, where it's more molecular than it is ionic, where they're sharing the electrons unequally. So you can either share unequally, actually don't even share, so no share. Oh, I guess, yeah, so no share goes over here. So the idea is that we can either share, not share, or share unequally. And we have a small rule for that based on electronegativity. So how do I tell ionic, polar covalent, and molecular apart? Well, the idea is that we compare electronegativities. If the change in electronegativity is, or the difference in electronegativity is greater than 2.0, it's ionic. If the change in electronegativity is between, oh gosh, where's my little notes? Just make sure I get the numbers right, otherwise I'm going to screw it up and I'll be bad. If it's between 1.5 and 2.0, oops, that's supposed to be 1.5 to 2.0, we're going to say that's polar covalent. And if the difference in electronegativity is less than 1.5, that is molecular. or covalent. Now, please note that different books and different websites define these differently. So what I kind of did is I took the average of them. I can't even remember which textbook I took this from anymore. I don't think it's your textbook necessarily. I don't even remember if I got it from a website, but I finally just said it's retarded to have 10 different definitions of this. So in Jay's classroom, this is the definition. You go take chemistry someplace else for some weird reason, and they tell you that, well, really it's only 1.7 to 2.0. Well, you go with that. Or if they say it has to be greater than 2.5, you go with that. You know, whatever rule the professor sets in that class or the book you're reading. In this class, we go by that rule. That's just one of those, I call them gray areas in chemistry, where it's not clearly defined. And so the gray area is pretty big. So we've got our polar covalent molecules. They behave like little bitty magnets. Boy, I just kind of want to push forward and finish that 11C homework. Okay, so let's just push forward. Well, it's good to break at a good point. And who knows, maybe we'll give you a Friday off before Thanksgiving or something, but we have to earn it by putting in the time. So, molecules, well, actually, let's just do it this way. Dipole or dipolar molecules are basically molecules that have an asymmetric distribution of charge. Molecules with, and I just like the word asymmetric. So an asymmetric distribution of charge sounds really fancy, but it simply means things like hydrogen fluoride, where one end is slightly negative and one end is slightly positive. Or it basically means that the molecule behaves like a magnet. So we call the attraction between two of these molecules a dipole attraction. Or I usually just am going to label that DD for dipole. Now what else does DD also stand for? And it's the size of battery, right? Double D's. So how do you tell whether we're talking about designated drivers, double displacement reactions, dipole-dipole interactions, or batteries? What? Or bras. Well, it's just the logical question should not be asked. Anyway, how do you know whether we're talking about those? Context, right? So it should be fairly obvious when, if we're in this chapter talking about the interactions between molecules and I say DD, I'm talking about dipole-dipole, not someone's bra size. And if I'm in chapter 8, I'm probably talking about double displacement reactions, right? And if I'm at the bar, I probably am talking about designated drivers. So depends on where you see me. When I say DD, you kind of know what I'm talking about. So dipole-dipole attractions is the attractive force between partial charges. Attractive force between molecules with dipoles. And so the idea is that if I have a hydrogen fluoride molecule and it's got one end that's slightly negative and one end that's slightly positive, that's going to be attracted to another molecule, that has one end slightly negative and one end slightly positive, that those are done. So this is what we call an or a dipole-dipole interaction. And it's between molecules. So that kind of makes sense, doesn't it, that magnets are attracted to each other? I should have brought my little magnetic models. I like sitting up here playing with them. And so for a dipole-dipole interaction to occur, we have to have a polar molecule. It's generally a weak attractive force. And it's proportional to the size of the dipole. Now, we're not going to worry about which molecules have the largest dipoles and which ones have the smallest. We're not going to ever calculate which, that sort of thing. We can do a simple calculation with differences in electronegativity. What's the question?
What does it say for size of the dipole?
Proportional. That's the proportional symbol. See, that's the little fish equals proportional to. So it means that it's proportional, meaning the larger the dipole, the larger the difference in electronegativity between atoms, the stronger that attractive force. Just like you can have little weak magnets and you can have really, really strong ass magnets. Okay, so we have 4 intermolecular forces. And I, of course, will never refer to them as intermolecular forces anymore. They are now called IMFs, which does not stand for International Monetary Fund or anything else. It stands for intermolecular forces. The first one is called London dispersion forces, after a guy named London. Or we abbreviate that LDF, which does not stand for anything else that I know of, does it? I don't know. Maybe some LDF stands for something else. And this is a general attractive force between all molecules. And the key here is it's between all. And it's proportional to the mass or the size of the molecule, meaning larger molecule, larger attractive force. And so, for instance, if I take a look at methane, which is just CH4 like this, that's going to be attracted to another CH4 molecule by this attractive force. This is by far the weakest force, or the weakest attractive force. So keep that in mind, that all molecules have it, but it's so weak that that if there's any other attractive force present, then that pretty much controls everything, and we don't have to worry about it. But it is there. And this is a big thing for second semester, and this crops up later on in this semester too. And it technically isn't in your book, so you have to kind of listen to the lecture for it. So let's see, is next week the weekend before Thanksgiving, or do we have one more week before Thanksgiving? Really? Holy shit. We have this week?
This weekend is nothing.
Right, okay.
Weekend is another weekend.
Right, okay. So we'll kind of have the break in the middle of chapter 12 or something, but that's, or 13 or whatever chapter we do next. That's okay. It's not a horrible chapter to have a break in. And it's best to get this out of the way before break. Okay, so the second attractive force is the one we just got done talking about, dipole, or DD. And again, that's between partial charges. And you have to have polar molecules. And that means that it's electrostatic, which means it's simply opposites attract. And it's a weak force but it's greater than LDF. So if you kind of think about the order we're doing things in, you'll notice that we're going to talk about them in the order of their strength. And an example of that is that HF molecule, or anything that has a positive charge or a negative charge and a partial positive. They can be attracted to another molecule. And then that fluorine could also be attracted to a second molecule if it wanted to be. Electrostatic simply means opposites attract. And I guess I should also put out that it's proportional to the size of the dipoles. We don't worry about that so much in this class simply because we can't calculate them. Okay, we have two more forces, one of which you already know, so really we have only one more new one, which is number 3. I should point out, favorite questions on things like this are, of course, draw me a picture, but don't draw me the picture used in your notes. And, you know, again, this crops up. It may be on this test. It may show up on the next test. It may show up in both tests. It shows up second semester. So it's one of those long-term stick them in your brains thing. Eventually, if I put it on 4 or 5 tests, usually everyone gets it by then because they figure, wow, you might put it on the next test. I better learn it. Okay, there's something called hydrogen bonding. And it turns out that hydrogen is the smallest atom, and it only has 1 electron. Therefore, it almost looks like just a plus charge. Meaning if I take a look at hydrogen, you know, there's the nucleus, and it's got 1 electron in an orbital. And if that electron is shared, then the other side of the molecule looks just like a proton. In fact, if we take a look at H+, that sometimes is called a proton, because it really is. If it's missing the electron, the H+ is really a proton. Just like a proton. Looks just like a proton. So if that electron is shared or missing, then. And it turns out that if we take a look at oxygen, nitrogen, and fluorine, nitrogen, these are the most electronegative small atoms on the chart. And so if we take those things together, and when we say that, which means that they really want, or that the shared electrons spend a lot of time around them. Just so you know, if I had to pick which one is the most important, the hydrogen bonding is the most important force. And we'll talk about it in several times, and it turns out to be, really, if hydrogen bonding didn't exist, or the concept of it, then, well, life on Earth wouldn't exist. So the idea is that if hydrogen is bonded to oxygen, nitrogen, or fluorine, which are essentially small, highly electronegative, so it's electronegative, small, then the dipole created is extra strong. It's greater than 10x what a normal dipole is. And so the idea is that hydrogen bonding really is just a special case of dipole-dipole. Special, extra strong. So we're going to draw it exactly like we would dipole-dipole interactions. Just realize that the key here is that it has to be hydrogen bonded to oxygen, nitrogen, or fluorine. And so classic example of that will be drawn next. Maybe I'm trying to crush this too much. Maybe I should have just gone a little bit slower, and then we could have done the lab on Tuesday, and then we could add the test next week on Thursday or something, but I don't know, probably be better to have the next lab. And who knows, maybe we'll even push it off till Thursday, although I have a feeling we'd do too much new material, and so that would be confusing. Nah. We can have a review night if you guys want to set up a night. Then, Brittany, 9 o'clock it is. I know, Jay, you're just going to have to, we'll tape things for you. Hopefully you can watch those on the road.
I didn't know how to get to that. I would look for that, but I could not find.
I'll show you after class here in a second. It's should be, well, yeah. So for dipole-dipole interactions, the classic example is water, because that's hydrogen bonded, or hydrogen's bonded to an oxygen. That hydrogen is bonded or attracted to, I shouldn't say bonded. I got to be careful. Hydrogen bond doesn't imply they're sharing electrons. It's just an attraction between them. And then, for instance, that hydrogen can be attracted to another water molecule, and that hydrogen is attracted to another water molecule. And so all these water molecules are attracted to each other. So there's my IMF. You know, we've got our partial positives, our partial negative charges. And so notice that it's hydrogen bonded to oxygen, nitrogen, or fluorine. Did you notice that both my other examples conveniently use carbon bonded to hydrogen? That didn't form a hydrogen bond, right? Because there's no separation of charge in them. Did you notice my dipole-dipole example was HF? That forms just the weak attractive force because fluorine, actually, that was a bad example. I should not have used hydrogen fluoride because that really is hydrogen bonding. We should go back. Jay's being an idiot. Bad example. Use your notes. They're there for a reason. So an example of one that would work like that is if I have some molecule like this. See, this is why I should have drawn it. So that hydrogen is attracted to the oxygen of another molecule because this is partially negative and that's partially positive. But it's not a hydrogen bond. See, this is a bad example because it's a hydrogen bond. Ugh, this is why I have notes. It's so I don't make stupid mistakes like that. And then the last attractive force, oh, come on. I'm not drawing that fast.
How do you know that little like S thing? How do you know?
That's from the electronegativity table. So if you look up the electronegativity of oxygen, it's like 3.5, and hydrogen is 2.1. So since the larger value is with the oxygen, the partial negative charge is with the oxygen, and the partial positive charge is with the hydrogen. So the more electronegative something is, the bigger that value is, the more negative it's going to be. And the smaller that value, the more positive it is, or the smaller that value is, the more likely that is to be the positive end of the molecule. One last one, and see, we already know number 4. That's simply ionic, meaning you gain, lose attraction, or gain, lose electrons. It means that it's electrostatic. And the classic example of that is simply sodium chloride. That the IMF between that is essentially also what we call a bond for ionic molecules. And so the 4 attractive forces that hold things together that are between molecules are basically London dispersion forces, dipole-dipole, and hydrogen bonding. And I got to be honest, ionic, some books will list it as an intermolecular force. Some books will list it as simply being an attractive force between atoms, because technically it's not between the molecules. But I like to throw it in there because it's the ultimate example of the electrostatic attraction, meaning LDFs mean no attractive force based on charge. Dipole-dipole has weak attractive forces based on separation of charge. Hydrogen bonding is bigger, and then the logical or the extreme conclusion to that is positive and minus from a ionic molecule. And we'll call it quits for that. So let me stop my recording.